Alright, so sorry I couldn't be with you in person today, but I'll try to make up for it with this little video. I just wanted to share with you a couple of results that we have for polynomial graphing and factoring. I'll make a scan of this document we're looking over here and post it in course content for you guys. And so the first theorem I want to share with you, well, I should say first of all, we've already talked about the factor theorem, which is certainly more important than what I'm sharing with you today. I mean, factor theorem is our biggest result that we really need to understand. So I'll get back to the factor theorem again when we meet in person. But for this time, let's talk about the rational roots theorem, or rational zeros theorem. Here's what it says. F a polynomial function, degree 1 or higher, and you have the usual standard form, where a sub n and a sub 0 are both non-zero, so the constant coefficient and the leading coefficient both non-zero. And all the coefficients are integers, right? That means that they're like plus or minus 1 or plus or minus 2 or 0, stuff like that. Then if a rational number is the 0, if f of p over q is equal to 0, then it must be that p is a factor of the constant coefficient, and it must be that q is a factor of the leading coefficient. This is the rational zeros theorem. Here it's assumed that p and q are sort of like reduced. Like if p over q, we wouldn't say p over q is 3/6. We would rewrite it as like a half. So it's understood that p over q are in their quote-unquote lowest form. So here as an example, well, let me just say what that means. So what that means is that we should look at possible ratios formed by the factors of the constant coefficients over the factors of the leading coefficient. In particular, if there are rational roots for f of x, then they'll be in that list. Now, of course, we have seen polynomials which have zeros, which are like square root of 2 or something like that, and those wouldn't be rational. But if they are rational, meaning that they're formed by fractions of whole numbers or they're negatives, then we should find them with this rational roots theorem. Okay, so here's an example that's kind of, this example is a little bit, well, it's not too interesting really, because we could use the quadratic completing the square idea for this one directly, but I'm going to just go through the motions here and use the rational roots theorem to try to understand it. So f of x is 6x squared plus 7x minus 5. Our goal is to factor this completely, all right? So notice that the leading coefficient is 6, and the constant coefficient is 5, right? So we can write 6 as like 3 times 2, or minus 3 times minus 2, or also 6 times 1, or minus 1 times minus 6. And minus 5 we could either write as minus 1 times 5, or 1 times minus 5. And so, if you think about it, then that means we should consider ratios of, again, the constant coefficient for the top and the factors of the leading coefficient for the denominator. I see I missed one, right? What is also here is 1 times 6, right? So we could also have 1 as a possibility, plus or minus 1 actually. All right. So, all right. And if we calculate f of 1/3, so I started with 1/3 actually. I usually start with plus or minus 1 because those are easier. I mean, what is f of 1? 6 plus 7 minus 5, which is 13 minus 5, which is 8. That's not 0. And f of minus 1 is also non-zero, because f of minus 1 would be like 6 minus 7 minus 5. In any event, so f of 1/3, and so we need to make a common denominator. Right, f of 1/3 is 6/9. So the 9 is coming from 1/3 squared is 1/9, right? So 6/9. 7 times 1/3 is 7/3 minus 5. So I'll make a common denominator of 9. So the 6 stays put. The 7 times 3 gives me 21. 5 times 9 gives me 45. And so I get this, which is not 0. So that wasn't a 0. That wasn't a root. And likewise, minus 1/3 doesn't give me a root. But something cool happens when we get to a half. When we plug in a half, we get 6 6 quarters plus 7 halves minus 5, which is 6 plus 14 minus 20 over 4, which is 20 minus 20 over 4, which is 0. So that tells me that 1/2 is a rational 0 of this polynomial. And so what that means then is by the factor theorem, right, we can factor out x minus 1/2. But, you know, that's going to be a pain. It's much easier to think of x minus 1/2 as 2x minus 1. Like if we can pull out that factor, we could also pull out this factor. We just have to have a number, right? So you can always like multiply one of these ugly things by a number to look for that, and do the math that way. So I'm gonna do it that way to avoid fractions, basically. And so if you look at it, 2x minus 1, and then the other factor is going to be 3x minus 5. Now, I could just see that from looking at the original polynomial, you know. So, you know, I don't know if you can see them both in the same frame. Yeah, I think we can see it, right? So, you know, I can look at this up here, right? And I can see that it factors like that just by guess and check. But I knew to look for the 2x minus 1 because I knew that f of 1/2 was 0. Now, if you didn't see how to get that, you could, of course, use our usual trick from last lecture, which was to take the polynomial and divide by 2x minus 1. And when we do that, we get 3x plus 5, just like that with a long division. And then, of course, we could either write it like this, but if we want to write in the format like x minus c, then we can factor out a 2, we can factor out a 3, and we get x minus 1/2 times x minus 5/3. So in fact, this polynomial has rational zeros of 1/2 and 5/3. And notice that those were in our list of possible rational zeros, right? 1/2 over here, 5/3 over here, but there's also all the other ones, like plus or minus 1, plus or minus 1/3, plus or minus 1/6, plus or minus 5/2, plus or minus 5/6. So this is the trouble with the rational roots theorem, is it doesn't just tell you what you're looking for, it gives you this laundry list of possibilities. Only, you know, maybe a couple which are going to actually be interesting. And then, of course, the other trouble is it could be that you have a polynomial which just doesn't even have a rational number as a 0, so it could be kind of just wasting your time. But anyway, it is a tool we can use, so I'll show you another sort of well, I would say this next example is pretty tough. All right, so it's going to take me a minute or two to talk through here. It would take me probably a solid half hour of class time to write this one on a board. So f of x equals to 42x to the 4th minus 83x cubed plus 52x squared minus 13x plus 1. Oh, that's quite a mess, isn't it? So this one is interesting because the rational roots theorem has something to say here. It says, well, the constant coefficient's 1, but the leading coefficient's 42, right? And 42 is 3 times 2 times 7. So you could look at it as 6 times 7, or 21 times 2, or 3 times 14, or 42 times 1. And so you got all kinds of rational zeros to look for here. Plus or minus 1, plus or minus 1/2, plus or minus 1/3, plus or minus 1/7, plus or minus 14th, plus or minus 1/21, plus or minus 1/42. These are all the possible rational zeros. All right, now we can use the factor theorem for guidance, of course. F of c equals to 0 if and only if x minus c is a factor. So we'll begin with the easiest number. All right, f of 1. Oh, hey, that's 0. Great. So we can use that to factor out x minus 1, right? I'll use long division like I did in the last class. Let me scooch this up a bit here. And so here's the long division. All right, so I start out by putting a 42 here, because then 42x cubed, rather, times x minus 1 gives me 42x to the 4th minus 42x cubed. I subtract. That gets me minus 41x cubed plus 53x squared minus 13x plus 1. So to get a minus 41x cubed, I need to minus 41x squared times that, which gives me this. When I subtract, I'm left with 12x squared minus 13x plus 1. And then, let's see here, to get to 12x squared, I have to multiply that by 12x. And when I multiply that, 12x times x minus 1, it gives me this 12x squared minus 12x. I subtract again. This time the 12x squared is canceled, and 13 minus a minus 12 is really 13 minus 13 plus 12, which is just minus x. The 1 comes down, and happy day, we have minus x plus 1, which is exactly the negative of that. So we put a minus 1 here. Got a remainder of 0. That's good. We better get a remainder of 0, otherwise we're contradicting that remainder theorem. Remember, the remainder theorem says that this remainder is f of 1 in this context. F of 1 was 0, though we figured that out before. And so in short, we just figured out that, f of x is x minus 1 times, f of x was the 42x to the 4th minus 83x cubed plus 53x squared minus 13x plus 1. And so we divided by x minus 1, and we got this up here. So that means that f of x is x minus 1 times this monstrosity right here, right? So we factor that out. But now we still need to break this thing down, right? So I'm going to call that f2 of x, just to give it a name. How to factor this? Oh, more trouble. Notice that f2 of minus 1 and f2 of 1 are both non-zero, so that's no help. But fortunately, my good fortune, right? If I plug in 1/2 into the f2 of 1/2 gives me, by this arithmetic right here, 0. So that's 43 times 1/2 cubed, which is 42. 42 times 1/2 cubed, which is 42 over 8. 1/2 squared is 1/4, so that's 41 over 4. 12 times 1/2 is 12 over 2, and minus 1 is minus 1, so that's f2 of 1/2. And then I make a common denominator of 8. It means I have to multiply the 41 by 2, I have to multiply the 12 by 4, I have to multiply the minus 1 by 8. And when I do that, I end up with, 96 minus 90, 90 minus 90 rather, which is 0 over 8. So what this means is that x minus 1/2 is a factor of f2 of x. So we can look for a 2x minus 1 to factor out to make life easier, right? Well, this is just a nasty example, right? But anyway, so continuing, this is a pretty tough example, all right? So factoring 2x minus 1 out from f2 of x, which is 42x cubed minus 41x squared, plus 12x minus 1, we got, we can use long division again to divide. So I do. We get a remainder of 0, that's a good sign. Let's see here, so let's go through this. So I'm dividing 2x minus 1 into this. So first of all, 21x squared times 2x minus 1 gives me 42x cubed minus 21x squared. So I subtract, I'm left with minus 41 plus 21, which is minus 20x squared. And plus 12x minus 1, bring those down, right? And let's see here, to get minus 20x squared from 2x, I need a minus 10x. So that gives me that minus 20x squared. It also gives me a minus times minus, which is plus 10x. And so you subtract, you get 2x minus 1, which is good because that's what we have here, so we just need plus 1 to cancel that out. And there you have it. We have factored the f2 of x. So we factored f2 of x into 2x minus 1 times 21x squared minus 10x plus 1. We're down to a quadratic, which means we could complete the square, or we could possibly just factor it by sight. I think I choose to factor it by sight here because it just was pretty clear. That 21x squared minus 10x plus 1 would be 3x minus 1 times 7x minus 1. I'm drawing the red in here. I know first I drew down the 3x and the 7x from the 21x. And then I thought about what I had to put there. It's either 1 and 1 or minus 1 and minus 1 because I got a 1 here. But since I got a minus, it has to be minus and minus like that. And so there you have it. F of x is x minus 1 times 2x minus 1 times 3x minus 1 times 7x minus 1. And we factored it. And you could pull a 42 out of that and get it, rewrite it in that form if you like. Actually, either one of these, I think, are completely fine answers. The nice thing about the boxed one is that you can see that the zeros of f of x are 1, 1/2, 1/3, and 1/7, which is nice if you want to graph it. right? Which is, of course, what we'll be getting back to next class. I don't really have anything much to say about graphing in this particular lecture because I'm focused in on the rational roots theorem and a couple of other sort of theoretical tidbits that I haven't shared with you yet. So I thought it would be nice to have another example which wasn't quite so horrible. So this is my example 3. And so hopefully this one's not quite as bad. We'll see. So x cubed minus 2x squared minus 9x plus 18. So rational roots here, it says I need to have factors of 18 over factors of 1. Well, factors of 1 are 1 and minus 1, right? So we end up with just with this plus or minus possible factors of 18, which are 1, 2, 3, that's a 6, and 9. Or, of course, I mean, obviously, I forgot about this one, but plus or minus 18, those are factors of 18. 18 times 1 is a factorization of 18 in this world. Okay, so then I just start calculating them, like f of 1, f of minus 1, you know, f of 2. Oh, f of 2 is 0. Woohoo! F of 3 was 0. Hey, great, now we got 2 of them. And f of minus 3 was also 0. So at this point, if you know what you're doing, you know you're done, because if we've got a cubic polynomial and we just found 1, 2, 3 distinct zeros, that means that we've got 3 factors. That's all we need, right? Because, well, put it together, right? Put the pieces together here. F of 2 being 0 means x minus 2 is factor of f of x. F of 3 being 0 means x minus 3 is a factor of f of x. F of minus 3 being 0 means that x plus 3 is a factor of f of x. And so the leading coefficient of 1, which means it has to be the product of these guys. Now, you can try it, multiply these out, and see if you don't get back to that, you know, the original polynomial. But there it is. Of course, we could do like in example 2, and instead take, divide x minus 2 into the polynomial. And when we did, we get x squared minus 9 as its cofactor. And so we have f of x is, you know, x squared minus 2, x minus 2 rather times x squared minus 9, which of course factors difference of squares by x minus 2 times x minus 3 times x plus 3. And then of course there, got it again, you know. But the cool thing about the rational roots theorem is it gives you some insight as to what are good guesses, especially if you have a kind instructor who says something like use the rational roots theorem, or perhaps all of the zeros are integers. Integers are particular examples of rational numbers, like counting numbers like 2, 3, 4, 5. These are actually rational numbers because they're a silly fraction. Like 2 is 2 over 1, so it's a rational number. Excuse me. So next up here, so rational roots theorem is sometimes helpful. But there's another idea. Oh man. Well, just a second, folks. I seem to have displaced my page 5. One moment. All right. Here it is. Page 5, we have a couple of more. Well, the first one I would say, I'm not advocating you think about this too much. I'm not sure it's really that helpful to us, but I just wanted to mention it. So I don't know if I even have any homework which is really on this for you guys. You know, but it's kind of a curiosity. It's worth at least mentioning. So this is called Descartes' rule of signs. And the result is this. If you have a polynomial, you can look at the number of positive real zeros of f. It equals the number of variations of sign of the non-zero coefficients of f of x, or less that number by an even integer. And likewise, to determine the number of negative real zeros of a polynomial, you can look at the number of variations of the non-zero coefficients of f of minus x, and it's either that or it's less, that number less an even integer, take away an even integer. So here's an example. So here we have a polynomial, all right, 3x to the sixth minus 4x to the fourth plus 3x cubed plus 2x squared minus x minus 3. So if you look at the signs, you got plus, minus, 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 right? So there are three places where you change from plus to minus or minus to plus. And Descartes' rule of signs says that there's either 1 or 3 positive zeros for f of x because of that. And likewise, f of minus x, that just flips the signs on the odd powers, but it leaves the even ones alone. So that gives you the pattern plus, minus, minus, plus, plus, minus as it happens. And so again, we just have 3 sign flips. So there's 3 variations in sign, which means again there's either 1 or 3 real negative zeros for f of x. So it's kind of an interesting result. I really don't have much more to say about that than that. What's next here is in fact much easier to understand, remember, and you might just intuitively think about this anyway. This is called the intermediate value theorem. The intermediate value theorem says that if you have x1 less than x2 and f of x1 is less than n, which is the intermediate value, this n is that intermediate value the theorem is speaking of. So if n is between f of x1 and f of x2, then there exists c between x1 and x2 for which f of c is equal to n. And if the value at x2 was smaller than the value at x1, it would still be the same. Like basically the point is if n is between f of x1 and f of x2, then there is a c between x1 and x2 which matches that value. Now, this is true for polynomials, but more generally it's true for what are called continuous functions. But for us, polynomials is what we're interested in. And actually, that's an important point because you've got to be careful using this on rational functions because rational functions are not continuous everywhere. They have these vertical asymptotes that are places where the sign can jump. But for polynomials, they have to be continuous everywhere. So here's basically a picture of the theorem, kind of a small picture, but if f of x1 is here and f of x2 is there, and then n is a value between those, then there has to be some c in between x1 and x2 such that f of c hits that n, right? So right there, f of c equals to n. Now there could be more than one, right? But the typical use of the intermediate value theorem is just to look for places where you change from negative to positive or positive to negative, because if you see that, that means that there's a point in between those two where there has to be a root, there has to be a zero of the function. So I tried to do some numerical work here for the previous polynomial. This guy, this 3x to the sixth plus minus 4x to the fourth plus 7x, this guy right here, all right? And when I plugged in some numbers, I did find some kind of interesting stuff. I mean, f of 1 was 0. Well, that's kind of cool. F of 1, 0. Well, there's 1, there's a 0. F of 0 was minus 3. F of minus 1 was minus 4. And at that point, I kind of got tired of it. And I said, well, what about 100? If I plug in 100, I get a large positive number. If I put in minus 100, I get a large positive number. Because if you look at it, I mean, just think about the formula, right? If you plug in 100 into this, 100 to the sixth power is way bigger than any of this other stuff. So it's going to totally dominate. Basically, this is like the dominant term for x, pretty big. And so because of that, without even doing any more calculator work, I could tell from the intermediate value theorem that there has to be some r between minus 100 and minus 1. See, because minus 100 is a large positive number, and f of minus 1 is minus 4, right? So somewhere between minus 1 and minus 100, there's got to be a place where it goes to 0 because it's changing from minus to plus in this interval, minus 1, 100 to 1, minus 1. Okay, well, I don't think that's a great example. Let me show you actually sort of a well-known algorithm for how we can solve a function which is continuous. And this method I'm about to show you is called bisection. And I'll talk about it for a polynomial, but it could equally well be applied to any continuous function on a closed interval. Suppose you want to find places where that function's 0, if it's possible, right? Well, first of all, if you just plug in a or b and you get 0, well, you're done, right? It's kind of silly. Otherwise, let x1 be the midpoint, and then calculate the midpoint, right? And then step 3, like if there's a sign flip from f of a to x1, then make your x2 the midpoint of x1 and a. And then you calculate f of x2. And if there's a sign flip from f of x1 to b, f of b, then you make your x2 the midpoint of x1 and b. And then you find f of x2. And you just continue each time, zooming in to the location where there's a sign flip, all right? And so I think that algorithm, it's easy to hear a person say, but it's much better to see it on an example. So let's look at it. Here's one. F of x is 10x squared plus 8x minus 24. So I'm going to look at trying to see, is there a 0 on between 0 and 2? Okay, that's the question I'm asking. Can we solve f of x equals to 0 for 0 less than or equal to x less than or equal to 2? All right. And so the answer to that question is yes. Yes, we can, and you can see that from just plugging in the endpoints, because f of 0 is minus 24, whereas f of 2 is 32, so there's a sign flip. So the intermediate value theorem says between 0 and 2 there has to be a place where the function's 0. All right, so I calculate the midpoint, that's 1. And so f of 1 turns out is minus 6. Right, so at that point, I'll draw a number line here. The number line can kind of help you understand what's going on. So we minus 24, we got 3.2, we got a minus 6 in the middle. So I'm not going to zoom in over here because it's negative, right? I'm going to zoom in over here because that's where I got a sign flip. So I next calculate the midpoint of 1 and 2, which is 1.5. When I plug in 1.5, I get 10.5. So then I see there's a sign flip between 1 and 1.5. Which means my x3 is going to be the midpoint of 1 and 1.5, which is 1.25. And then guess what I do? I plug in 1.25 into the function. I get 1.625. So that shows me that there is a sign change between minus 1 and 1.25. So I'm going to go and zoom in further, midpoint of 1 and 1.25. That's giving you 1.125. Okay, great. I plug in, I evaluate the function at 1.125. I get minus 2.34. Aha! So there's a sign flip between 1.125 and 1.25. So I'm going to take the midpoint of those guys. I can see it on my... I'll just scooch this up a bit here. So I take the midpoint of 1.25 and 1.125 and 1.25, and that gives me 1.875. And I plug that into the function, I get a minus 0.4, which then says I need to look between 1.875 and 1.25. I take that and find the midpoint, that's 1.21875. I calculate f of 1.21875, I get 0.6. So, okay, so that means that the answer has to be between or at least an answer has to be between 1.1875 and 1.21875 roughly. So I take the midpoint of those, that's my 7th iterate, and that gives me 1.203. And at this point I've run out of paper, so we're gonna have to let that be our answer. But f of 1.203 is about 0.099. And that's pretty close to the right answer, because I made up this example by putting x minus 1.2 as a factor. So actually, if you calculate it exactly, you know, the man behind the curtain, you know, full disclosure, actually, f of 1.2, exactly 1.2 is equal to 0. So, you know, you can see that this bisection method, it works pretty good. And, of course, you could do this with a graphing calculator, right? That's what we do. If you want to find where a polynomial is 0, you just zoom in and you get closer and closer and closer to where you see that the graph is crossing from negative to positive. Well, that's exactly what this is. This is this bisection method. It's zooming in to where there's a change in sign, and that shows us where the 0 is. And that's based on, again, something called the intermediate value theorem. So, hey, that's what I got for you guys today. Sorry this didn't take the whole time, but, you know, I hope you've maybe paused and written some things out, because, I don't know, I personally probably couldn't take notes as fast as I just talked. But on the other hand, I do have a PDF of this for you to follow along, so I will say all this in the announcement. Anyway, hope you guys enjoyed, and I'll hope to see you again Wednesday. Thanks.